Okay, the next topic is principle of inclusion, exclusion, or your book also calls it subtraction rule. Principle of inclusion, exclusion for two sets, also called the subtraction rule. So let's see what this rule says. So suppose that a task can be performed in, let's say, n1 ways. Can be performed either in n1 ways or in n2 ways. Then to perform this task, we have n1 plus n2 minus number of common ways to perform this test. We have this many ways. So it could be a little bit confusing, especially when you compare it with the product rule. However, don't worry, I'm going to explain about this. So first of all, in the product rule, we had few tasks. For example, we had at least two tasks. Let's say we said, okay, let's say we want to choose lunch and dinner. So two tasks, choosing lunch and choosing dinner. And then task one, we had n1 ways, task two, n2 ways. Then in total, we have n1 times n2 ways. Now, this one, there is addition involved. Now, what is the difference? This time we have one task to perform. Now, for this one task, we have either we can do it with n1 ways or n2 ways. And to perform the task, we have n1 plus n2 minus number of common ways to do the task. So in the example of the food that we said, so instead of having lunch and dinner, let's say this time we only focus on lunch. So just one task. We only focus on lunch, but that one task can be performed either in n1 ways or n2 ways. So suppose, let me write down the example. Suppose that for lunch, for lunch preparation, we can have three foods with chicken in them, or let's say 4 foods with mushroom in them. And suppose that only one of these foods contains both chicken and mushroom. In how many ways can we prepare the lunch? So one task, preparing lunch, we can either do it with 3 foods with chicken or 4 foods with mushroom. So in total, we will have 3 plus 4, just one task. 3 plus 4 minus number of common ways. So how many ways? How many? So common ways. So we have 2 ways, either with chicken or with mushroom. So how many common foods that we have? In other words, how many foods do we have that they have both chicken and mushroom? There's only one food. So there's only one food that's a common way, meaning that because one way was to go with chicken, one way was to go with mushroom. So the common way means both chicken and mushroom. There's only one food that has this feature. So in total, to prepare the lunch, how many options do we have? So we can prepare, so let's say by the principle of inclusion, exclusion, mentioned above. We have 3 plus 4 minus 1 equals 6 options to prepare the lunch. In total, we have 6 options because one of the options was the common one. Right? So if I call them, for example, food 1, let's say food 1 is the food that has both chicken and mushroom. Then we have food 1, food 2, food 3. But then these 4 foods with mushroom, one of them is already food 1. So then I have food 4, food 5, food 6. Yeah, so these 4 foods have mushroom, right? And these 3 foods have chicken. So these 3 foods chicken. And these 4 foods mushroom. And 1 food is common. And in total, we have six foods for our lunch preparation. 3 plus 4 minus number of common ways. 1 is common. One of them is common. So 3 plus 4 minus 1 are 6 foods to choose for lunch. Okay, now again, we can state this principle of inclusion exclusion using set theory notation. So again, I can mention as a remark. So the principle of inclusion, exclusion. And of course, for 2 sets, can be phrased as follows. So we can say that number of elements, let's say in A1 union A2 is equal to number of elements in A1 plus number of elements in A2 minus number of elements in the intersection of A1 and A2. So let's say if you have A1 and two sets, A1 and A2, let's say one of them with N1 elements, one of them with N2 elements. How many elements will we have in the union? Number of elements in A1 plus number of elements in A2. But when you can calculate number of elements in A1 plus number of elements in A2, then the number of common elements have been counted twice, right? Because in A1 union A2, the common elements will appear only once, right? So in the left-hand side, we have to count every element only once. And definitely also the common elements also we have to count it once. But when we look at the right-hand side, now if you include only the first two terms, then the common elements will be counted twice. One time as the element of A1, one time as elements of A2. But we don't want to count twice. We want to count only once. Therefore, we subtract with the number of common elements, because up to this point we have counted it twice. But when we subtract it once, then overall we are counting the common elements only once. And also other elements, we are counting them only once. And that's exactly what we want to do. So in example above, so if you want to use this notation in example above, we can set, for example, A1 to be, remember we had food, 3 foods with chicken, 4 foods with mushroom. So food 1, food 2, food 3 for A1. Foods with chicken. So chicken, and A2 was food 1, food 4, food 5, food 6. So these are foods with mushroom. And number of elements in A1 union A2 is going to be number of elements in A1 plus number of elements in A2 minus number of elements in the intersection. In A1, I have 3 elements. In A2, I have 4 elements. In the intersection, I have 1 element, right? A1 intersection A2 obviously is just F1, the set containing F1. So it has 1 element only. And the answer is 6, which is what we found above. Okay, let's look at another example. How many elements or how many positive integers less than or equal to 100 are divisible by 3 or 7. Let's say if you want to count how many elements, how many numbers, how many positive integers less than or equal to 100 are divisible by 3 or 7. So let's use the set theory notation. So let's say if I call, for example, A1 to be the set of all elements, let's say n in n, such that n is less than or equal to 100, and let's say 3 divides n. A2 n in n n less than equal to 100, and 7 divides n. So A1, we defined it as number of elements, number of natural numbers that are less than equal to 100 and are divisible by 3. A2 are the set of, so A1 is the set of natural numbers which are less than equal to 100 and divisible by 3. A2 is the set of natural numbers which are less than equal to 100 and are divisible by 7. And then what do we want to find? We want to find number of elements in A1 union A2. So what do we know by principle of inclusion exclusion? By principle of inclusion exclusion, number of elements in A1 union A2 is equal to number of elements in A1 plus number of elements in A2 minus number of elements in the intersection. Now in A1, how many elements do I have? A1 is the set of all numbers less than equal to 100 which are divisible by 3. So what are that gonna be? So A1, which elements less than equal to 100 are divisible by 3? 3 itself, 6, 9, right? And all the way to 3 times 33, which is 99. So that's the last one. So how can we calculate basically? So this one has, A1 has 33 elements, obviously, right? So 3 means 3 times 1, 6 means 3 times 2, 3 times 3. And the last one is 3 times 33. So, but in general, what will be the recipe to find the number of elements in such a set? You know, let's say number is less than equal to the set of numbers less than equal to some fixed number, which are divisible by some other fixed number. How can we calculate it? So number of elements in A1 number of elements in A1 is equal to 33, which is same as, so 33 is the number that I can find by dividing 100 over 3. So remember, A1 was numbers less than equal to 100, which are divisible by 3. Now, if I divide 100 by 3, I get 33 point something, right? So if I take floor of it, then I'll get 33. So this recipe is always valid. So let me, maybe I can leave as exercise that and check that, let's say if you have a set A, which is n, the number of the set of all positive integers that are less than or equal to, let's say, some number, let's say n0 with d divides n, then the number of elements in A will be the floor of n0 divided by d. Okay. So you can check this. Now A1 has 33 elements. So similarly, A2 has how many elements? According to this rule that we said, numbers less than or equal to 100, which are divisible by 7. So my n0 again is 100. My d this time is 7. So I can say that the floor of 100. The floor of 100 divided by 7. I think this is going to be 14. And what about A1 intersection A2? Next, for A1 intersection A2. A1 is the set of all elements that are less than or equal to 100 divisible by 3. A2 less than or equal to 100 again, this time divisible by 7. So if a number is in both A1 and A2, A1 intersection A2 means all common elements between A1 and A2. If a number is in both A1 and A2, means that number will be both divisible by 3 and 7. So n in n such that n less than or equal to 100 and 3 divides n and 7 divides n as well. Then this is same as saying that n belongs to n such that n less than or equal to 100 and 21 divides n. Why is that true? See, because if 21 divides n, so let me call this one, for example, star, if I want to show that these two are equal. Let me call this one, for example, star, and let me call this one 2 star. Now, if 21 divides n, then 3 divides 21, and 21 divides n, so 3 divides n. And also 7 divides 21, and 21 divides n. So that means 7 divides n. So that means n belongs to star. So star, so 2 star is a subset of star. See, I'm claiming that these two sets are equal. How do you show that two sets are equal from previous chapters? A very basic fact from previous chapters is that if you want to show that two sets are equal, you have to show that the first set is a subset of second set and second set is a subset of first set. So how do I do that? First, I want to show that the second set is a subset of first set. So 2 star is a subset of 1 star. To do that, I took an element in 2 star. So if you take an element in 2 star, means you're considering an n value less than or equal to 100 with 21 divides n. So that's why I wrote 21 divides n. Then 3 divides 21 and 21 divides n. So 3 divides n according to the properties of divisibility. Transitive property, basically. 3 divides 21, 21 divides n, then 3 divides n. And similarly for 7, so 3 divides n and 7 divides n, which means my n will be in this set. So that's why I said n belongs to star. So if I take an element in 2 star, it will be in star. And that means 2 star is a subset of 1 star. Okay, now conversely, if n belongs to star, then that means n. So if I have an element here in star, then that means 3 divides n and 7 divides n. and 3 divides n, and 7 divides n. Now, let's consider the first fact. Now, 3 divides n means what? Means n, you can write n equal in the form of 3k for some integer k. And therefore, 7 divides 3k. This 7, I know that 7 divides n, right? And n is equal to 3k. So I can say that 7 divides 3k. And this means that 7 divides k. Why is that? Because we had a fact from before that if p divides ab, then p divides a or p divides b. If p is a prime number. So this is one of the most important properties of prime numbers, and one of the most fundamental properties, that if a prime number divides a b, product of two numbers, then either p divides a or p divides b. So here 7 divides 3 times k, and of course 7 does not divide 3, right? 7 is not a factor of 3, of course. Therefore 7 must divide k. P divides AB, then P divides A or P divides B. So if P divides AB and P does not divide A, then we must have P divides B. So in this case, 7 divides 3K and 7 does not divide 3. So 7 divides K. And therefore, this means that K, we can write K in the form of, let's say 7 times K prime for some integer K prime. So plug back, what do we get? Plug back. Then we get n. What was n? N was equal to 3k. And k was 7k prime. So 3 times 7 times k prime. And the answer is 21k prime. So n equals 21k prime. And that means 21 divides n, right? Because 21 is a factor of n, or 21 divides n, and that means n belongs to 2 star. Please remember 2 star was the set of all numbers less than or equal to 100, where 21 is a factor for them. So here, what did I do? I considered some number n in 1 star, meaning that 3 divides n and 7 divides n. After some calculation and using properties of prime numbers, I concluded that 21 divides n, and that means n belongs to 2 star. And what does that mean? So that means 1 star is a subset of 2 star, because if I consider one element in 1 star, it will be automatically in 2 star. So 1 star is a subset of 2 star. Therefore, we can say that 1 star is equal to 2 star. Okay. Okay, so we have shown that. We have shown that A1 intersection with A2 is equal to the set of all natural numbers such that n is less than or equal to 100, and 21 divides n. So that means number of elements in A1 intersection A2, according to the recipe that we said, n less than or equal to 100, and 21 is a factor of them. So I just need to take the floor of 100 divided by 21. This is 4 point something, so the answer is 4. Thus, the number of numbers, positive integers, number of positive integers less than or equal to 100, and divisible by 3 or 7. It's going to be 100 divided by 3. The number of elements in A1 union A2. Said number of elements in A1 plus number of elements in A2 minus number of elements in A1 intersection A2. So that's, we said 100 divided by 3, 100 divided by 7, minus 100 divided by 21. And the answer was 33 plus. The other number was 14. And then the other number is minus 4. So this is 43. 43 numbers less than or equal to 100 are divisible either by 3 or 7. Okay, so now let's look at another example. Suppose that a company receives, let's say, 230 applications. Suppose that 52 applicants are majored in mathematics. Mathematics, 61 applicants majored in computer science. And 6 applicants are double majored. Double majored in mathematics and computer science. Computer science. Find the number of applicants which are which are majored neither in computer science nor in mathematics. So to solve this type of problem, the very first thing I suggest you to do is that choose set theory notations. So you can choose, for example, capital letters A1, A2, and so on for your sets here. So we have few sets here. One set is the set of all applicants majored in mathematics. One set applicants, all applicants majored in computer science. So let me give notation. So let's say let A1 be the set of all applicants majored in computer science, let's say. A2 is the set of all applicants majored in all applicants majored in mathematics. And we want to find number of elements. Want to find number of elements in A1 intersection, A1 complement intersection A2 complement. We want to know how many elements, how many applicants are neither majored neither in computer science nor in mathematics. So we want the applicants that are not in A1, which means they are in A1 complement, and means intersection. They are not in A2. Not in A2 means A2 complement. We want to know how many. So this how many means the number of elements in which set in A1 complements, the applicants that are not in mathematics, and it means intersection, not in computer science. A2 complement means A2 complement. So we want to find the set of these elements. So note A1 complement intersection A2 complement is same as A1 union A2, the whole complement, right? By De Morgan's law. Now, if I want to find the number of elements in A1 union A2, so how many elements do we have in A1 union A2? So that's number of elements in A1 plus number of elements in A2 minus number of elements in the intersection, which is by principle of inclusion, exclusion. How many elements do we have in A1? A1 was majored in computer science. We had 61 of them and 52 of them in mathematics, and there are only 6 of them which are common or double majored. So this is 112, 113 minus 6, that's 107. So 107, so these are the element or the applicants which are majored either in computer science or in mathematics. So that's the A1 union A2. Now what do I want? A1 union A2 complement. So lastly, the number of elements in A1 union A2 complement is same as number of elements in the universal set minus number of elements in A1 union A2. As a minus number of elements in A1 union A2 itself. So number of elements in a complement of a set is the number of elements in the universal set minus the number of elements in the set itself, right? So this is, let's say, if this is U universal set, and let's say you have a set B, for example. So if you want to know number of elements in B complement means this area. You can easily do it. Just find the number of elements in U minus number of elements in B. That gives number of elements in B complement. So what is that going to be? So number of elements in A1 union A2 complement. In the universal set, how many applicants do we have in total? In total, we had 230 applicants. Minus A1 union A2 was 107. So that is going to be 123. So that's the final answer. Okay, I also want to mention about some specific cases of inclusion exclusion principle. So particular case of inclusion exclusion principle if A1 intersection A2 is equal to empty set, then what can I say about the number of elements in A1 union A2? Then in that case, the number of elements in A1 union A2 will be number of elements in A1 plus number of elements in A2. So remember we said that if you have one task and you can do it in either in one ways or in two ways, then to perform that task, you can add N1 with N2. To know in how many ways you can perform that task, you can add N1 and N2, but you have to subtract the common ways. Now, if A1 and A2 have no intersection, if the intersection is empty, then that means there's no common way. And therefore, you have to subtract basically 0, which we can ignore it. So number of elements in A1 union A2 in this case is number of elements in A1 plus number of elements in A2. We can also generalize this more generally. If let's say A1 to AN are sets such that AI intersection AJ equals empty for I not equal to J and I and J between 1 to N, i.e. A1 to AN are pairwise disjoint, then we can say that number of elements in A1 union to AN is number of elements in A1 plus ... number of elements in AN. So if there is no intersection between any two of them, then number of elements in the union will be the sum of number of elements. So we know that for two sets, if intersection is not empty, we know what to do. We have to just subtract the number of elements in A1 intersection A2. But for n sets, if the intersection is not empty, what should we do? What should we subtract? So in that case, the formula will be a little bit complicated and you will learn it in discrete mathematics 2. So note the general formula for A1 union to AN without assumption AI intersection AJ equals empty set for I not equal to J will be covered in Math 221 or Discrete Mathematics 2. So in this course, we just cover simple cases. Either for n sets, we cover it only in the case that any two of them have empty intersection. Then the number of elements in union is the sum of number of elements. You can also see it in the picture here. So let's say if you have A1 here and A2 here, and let's say A3 here, and let's say A4 here. So if there's no intersection between any two of them, then if you want to count the number of elements in the union, you just need to add number of elements in each AI. But if there is some intersection between, let's say, two of these, let's say if there's intersection between A1 and A2, or between A1 and A3, or between A1, A2, A3. In those cases, you will learn it in Discrete Mathematics 2 or Math 221. But for two sets, in the case of two sets, which is a simple case, we covered it both in the case that there is no intersection, which in that case, A1 union A2 will be A1 plus A2. The number of elements of A1 union A2 is number of elements in A1 plus number of elements in A2. And if there is intersection for two sets, we covered it. For two sets is what we call it principle of inclusion-exclusion, which is number of elements in A1 plus number of elements in A2 minus number of elements in the intersection. So the summary for two sets, we covered it both in general case, which is this, and also the particular case where the intersection is empty. For n sets, we only covered it in the particular sets where the intersection is empty for any two sets. The general case for the n sets will be covered in Math 221. Okay, so let's look at an example. Suppose that to go from city, let's say A, to city B, we can either, so let's say drive and go from A to B via cities, let's say D1 or D2 or D3, or fly and go from A to B via cities, let's say D4 or D5, or take a train and go from A to B via cities D6 or D7. So how many options do we have for the middle cities, for the middle city to go from A to B? So see, we have city A here, city B here. Then we have, let's say, D1, D2, D3, D4, D3, D4, and then D5, D5, D6, and D7. So D1 and D2, D1, D2, D3, if we drive, so this one, if we drive, D4, D5, if we fly, and the other two, if we take the train. So overall, how many options do we have for the middle cities? See, because there is no intersection between drive and fly, or drive and train, or fly and train. Therefore, we can use the this particular case that we said. And by the way, this particular case in your book is called sum rule. Your book calls it sum rule if you see this word or this term. So because there is no intersection between any two of them, we can use this sum rule. And to find the elements of union, just add the number of elements in each set. So if you want to use this notation, let's define our sets. So because first we need some sets and then we take the union. So let A1 equals, let's say D1, D2, D3, be the middle cities, be the set of middle cities. Middle cities if we drive. Similarly, A2 equals D4, D5. Instead of middle cities, if we fly, A3 equals D6, D7. Instead of middle cities, if we take a train. And then we can say that then since A1 intersection A2 is empty set, which is same as A1 intersection A3, which is same as A2 intersection A3. Any two of them that I consider have no intersection. Then since this, by the particular case above, we can say that the number of elements in A1 union A2 union A3 is number of elements in A1 plus number of elements in A2 plus number of elements in A3. So 3 plus 2 plus 2, which is equal to 7. So so this was the particular case of principle of inclusion-exclusion when there is no intersection between any two sets. In that case, we just simply need to add the number of elements in each set to get the number of elements in the union. Okay, guys, so this is about the first section about we covered the basic, some basic tools of counting. And next time we'll do a pigeonhole principle. Okay, so thank you and see you next time.